Hey everybody, welcome back to Daily Stand Up. In this video, we're going to do a mock system design interview where basically I'm going to show you an example of a pretty common problem, and we're going to walk through what a conversation might look like in a system design interview and how you can go about creating a solution for the problem. So we're going to go do it step by step. I'm going to talk about it as if I'm kind of being interviewed and how I would go about talking about the problem and showing you a potential solution. So the problem we are having here is that the REST API is intermittently throwing 504 error codes due to timeouts. So the requests are taking too long. We are currently sending 3,000 requests to the API per minute for a single user. We are posting location data to the database. So it sounds like we're trying to send up 3,000 requests to the REST API to post this location data to the database. But 3,000 requests, we're getting timeouts, so we're getting a bunch of 504 error codes back intermittently on the front end. I think that's the problem. So the desired state is that we want to scale the system for multiple users, greater than one. We want to be able to process more than 3,000 messages a minute, with, I guess, the minimum being 50,000 per minute with no timeout exceptions. How can we re-architect the system to handle this throughput? So if I'm understanding this correctly, the problem is we're using some front end, and it's tracking our location. It's getting some kind of location data. We're getting 3,000 of those data points, and we're trying to send that off to the database, and we're getting timeouts. So we need to fix this because we're going to get more users. We're going to be sending a lot more data points in the future. So one problem with REST APIs is that just due to the nature of requests and responses, they're limited on how much resources they consume. You get a lot of resource basically timeouts if you send up too many requests in a small enough window of time to REST APIs. You get a lot of timeouts, which is what you're seeing here. So it'd be impossible for us to scale beyond that 3,000 number currently with how the system is doing it. So it'd be tempting to want to you'd be tempted to want to do something like this and kind of like scale the REST API horizontally. Basically, well, I shouldn't copy that. It doesn't. You would be tempting to want to just continue to scale the API, right? Like just put on a bigger instance. If you're in the cloud, if it's AWS, you could put it on a larger EC2 instance or something like that. It's tempting to want to say that, but you will still run into the same issues regardless of how big your instance size is. So you really have to figure out a different solution rather than scaling this instance horizontally. So one potential solution to this is to introduce some kind of queue, meaning like a queue that our front end can just send messages up to and not worry about the state of when they're processed. Because if we're just posting location data up to a database, it shouldn't matter that we get a response back per se on the front end to say location data saved or whatever like that. And given that these are the parameters of the system, we can do that. So what I'm proposing here is we should introduce a queue. So let's go ahead and add a queue, and I'm going to make this yellow just to signify that it's new. So we're going to make a queue, and we'll call it, I guess, the in queue, meaning like the messages that are received into the queue. So what we're going to do is we're actually going to have the REST API, instead of talking directly to the database, we're going to have the REST API talk directly to this queue. Now you might be thinking like, wait a second, but the bottleneck is still at the REST API, and that's exactly right. We're going to change it actually. We're going to change it from being a REST API, and we're actually going to use WebSockets. So WebSockets, we're not going to experience that same timeout exceptions that we're seeing. We're not really concerned about resources now in the same way we were with REST APIs. So I'm going to write WebSockets here, copy that and paste it right there. So we're going to change, it can still be an API, but we're not, just for the sake of the diagram, we're just going to call it the backend now, just as a way to, distinguish it now. So we have this WebSocket connection from the front end to the back end, and we're sending data. So I'm going to just, we're sending our data. So I'm going to make that in red. We're sending our data from the front end to the back end via WebSockets. And now we're going to basically post that data to the in queue. So when our WebSocket method is triggered on the back end, we're going to send that over to the in queue to be processed at a later time. And now what we have here is a connection from the front end to the back end to this queue. Now the remaining connection is we have to get from the queue over to the database. And one way to do that, I mean, there's a couple different ways we could look at this. If we're looking at this as this is a cloud-hosted system, we could set up a trigger function. If it's AWS, we could set up like a cloud, some kind of cloud watch observer, basically to look at when a message is received in the queue and then trigger some form of Lambda function to post it to the database. We can set it up like that, but for the sake of this diagram, I'm going to assume that we're not entirely in a cloud-based solution. So I'm going to, that's my assumption. So I'm going to actually create another backend service, and we're just going to call this our queue processor. What the queue processor is responsible for is going to be to listen or subscribe to this in queue. So as a message is sent into the queue, is enqueued in that queue, the queue processor is going to receive that message because it's subscribed to our in queue, and then it's going to basically post it to the database. Just like this. So now we have this a little bit different flow. So now we're running from the front end to the back end. We're sending our data into this queue. And again, the front end now is not waiting on anything on the back end because we're using WebSockets, right? It doesn't matter. So we can we'll be able to exceed the 50,000 requests per minute limitation by far. Now this number is really irrelevant. We can send off so many messages from the front end, it doesn't matter. It matters in terms of how we process it from our queue processor over to the database. This connection here from the front end to the back end to the queue processor is perfect. That'll be able to handle a ton of messages, as many as we need. If we need to scale this more, we can always add another queue, and we can build this out. The remaining bottleneck we still have potentially is the connection from the queue processor posting the data over to the database, because we don't want to overload the database. If all of a sudden we're sending off 100,000 messages, they're in the in queue, then now they're processed by the queue processor. We don't want to send all those off, in the database. So a couple options, we might be able to create like some kind of batch process where we like batch the messages together and post them to the database. But honestly, we still might have a little bit of limitation there. We could scale the database again to a larger instance, or however the database is hosted. But for the sake of this diagram, I'm going to assume, just like I assume with my queue processor, I'm going to assume that the database is just hosted somewhere. It's just like a MySQL database that just exists on some system where we don't really have the advantages of like an auto scaling environment in a cloud. Because if we had auto scaling set up, we could set up auto scaling for the backend, the queue processor or database to see if if resources or CPU or memory exceed a certain threshold, we could auto scale to the next instance size, and then vice versa as it needs to scale down. But I'm going to assume that we don't have access to all that because that stuff can be a luxury. So what we're going to do is we need to set up, unfortunately, well, maybe not unfortunately, we need to set up some kind of manual throttling for our queue processor's connection to the database. So we need to throttle that in to some degree. And we can actually just do that in code, so in our queue processor. So we just need to throttle the connection to the database. We don't want to exceed the connection pool that the database has. So I'm just going to say, I'll make a note of that to, we don't add logic to not exceed connection count. So databases, if you can be set up with a connection pool. Basically, you can specify a finite number of connections available to the database. And basically, what we're saying is that we don't want our queue processor to establish a new connection to the database every time a message comes into the queue processor, right? That's not good. So we need to establish a connection pool to say that, okay, per messages coming in, we have a finite number of connections that have been allocated to the database. Why this is important, right, is because you don't want to just leave a standing connection to the database just always open, but you also don't want to create a new connection every time we read a message off the queue. We want to have some kind of like connection pool in place, so that way we don't exceed the overall connections. So we just want to set up connection pooling. So we can say set up connection pooling. And then we also want to add, we just want to add some basic request limiting. So we can do that with semaphores. We can do that with something like that. We can just .NET. We can use a semaphore slim or something like that. Something to basically limit the number of requests that we're sending, essentially. I mean, there's other ways to do that, and that really semaphore really comes down to how many degrees of. Well, actually, let me rephrase that. We might not be able to. We may just have to. We could set up in a batch. We could do that. I'd like to experiment with using a semaphore actually to connect to the database, just to kind of limit that. But honestly, we should be fine with that, but I think we'd have to test that. So now we have this this queue processor processing the messages off the queue. We're going to add some logic in the code to basically throttle how many requests we're sending to the database. I think is really the bulk of what we're trying to say there. So I'm actually not going to specify any technical things. We're just going to say add request limiting. I think will be helpful. Okay, and now assuming we don't need, I don't know if we need any kind of like response back from like the process, but we should probably have some kind of fallback to say like, okay, if a request didn't make it into the database, we need some kind of fallback logic. So we're going to add another queue. We're going to say like or like an out queue or something. We could add like actually we're going to add two more queues. So I'm going to add a dead letter queue and an out queue. The out queue is going to give us the result of the processing. So basically, we're going to copy this, and now we're going to call this result. So, what was the status of the message that was posted to the database? So we sent some kind of location data to the database, and we're getting a result back from processing. So our queue processor posts it to the database. Is it successful? Yes. Let's send a response back to the out queue. The out queue then, we can create a subscriber or a consumer on the back end again. to talk to the out queue, and then again post the result back, to the front end via WebSockets in real time. So again, nothing is waiting on anything, and we have a good stream of communication happening, and the front end is not affected by any kind of waiting on the back end. So that should be super helpful. We need a dead letter queue for failed processor. We need a dead letter queue for any kind of messages that are not consumed by the queue processor for whatever reason. A lot of the times this is set up kind of automatically with queues, but how we're going to set it up, I think, is any well. So we're assuming, I think, in this structure, we're assuming that messages are going to be processed successfully. We should actually have. I'm actually going to change this to be a success queue. So if the message was successful, go to the success queue. And we're going to call this the failed queue. So basically, we're going to say we're going to give the success result back here. And we're going to go success result. And then we're going to move these failed results up to this failed queue. So if the processor detects that there has been a failed message that has been processed, we're going to go ahead and post that up to this fail letter queue. Okay. Then what we're going to do is, what happened to my, oh, did I get rid of those? I think I did. Okay, so this is a failed result. So for whatever reason, the message didn't make it in the database. We have to do something with it. So let's go ahead and post. I'm going to post the data back to the failed letter queue. Okay, the reason for that is because we still want it to be processed at some point. It doesn't really matter the time or the order it was processed in. We're not given that specification on the spec. So we don't, my assumption is that we don't care about the order that we process these in. Now that's an assumption. We have to validate that assumption in a real world system, right? You have to ask, does the order of message processing matter? If it does, this isn't going to work. If the order of messaging does not matter, and we can still use, and we can take advantage of asynchronous processing, then this will be fine, right? Because all we care about is, did the message get processed successfully? But again, that's an assumption, so we just have to, validate that. So what we can do is we have a fail letter queue, and I think, honestly, if we go ahead and copy this and go like this, we can connect it back to the back end and have a listener on the back end listen to that fail letter queue, get that data, and post it back to the in queue. I think we could really do that because we're not expecting to get a lot of failed letters. Failed. I'll just get failed. We're not expecting to get a lot of failed messages, but if we do, we have handling for that. And again, this presents a really, I think, good flow because it really, again, we're limiting connections to the database. We have an in queue for all the data that's coming from the front end, so we can, and again, with WebSockets, so it's as fast as we want it to be. So we can post hundreds, millions of messages in the in queue. The queue processor processes that as they come. So this will really, we have to pick a language for the queue processor to be able to process that efficiently. But we can get into the technical details when we actually write the stories. But with this, the queue processor, that's all it does. If for every success message we send it back to the success queue, that on its own time is consumed by the back end, sent down to the front end to say, hey, this was successful. If we get a message that wasn't successful, we send it up to a failed queue. The back end listens for that, sends it right back to the in queue. I think this will work. There might be some stuff that we'll have to iron out, but I really think that for the problem statement that we were given, I truly think that this could handle what we were trying to do. We can scale this for more than one user. we can process way more than 50,000 messages with no timeout exceptions. And again, this is what the problem. So you heard my assumptions, and I think that this could get us to that desired state. Now, obviously, we can probably optimize this another way. Maybe we could reduce a queue. Um, maybe you could even argue that you could establish a connection to the front end of the queue directly. But I was trying to maintain the connection to the back end just to take advantage of some back end things that .NET, if that's what we're using, can do for us. And we could probably set up our database to be in some kind of cloud environment in an auto scale group to maybe handle higher throughput to the database. So if we were to actually if this was, let me find a shape I can. Is there like an outline? If this was in AWS, we could put this in. Let me send it back. If this was an AWS, we could put this in an auto scaling group and then scale that instance as it, dynamically as we need to. So, but again, that's the assumption is that we're not in that kind of environment. But if we did, we could just tack that on, but there's a cost associated with that. So anyway, I think that this really is a step in the right direction. I don't think it's 100%, but I think that for the bare minimum requirements, I think that it'll at least get us to a position where we can process those 50,000 messages per minute for the system. So I think that's it. I think that's my answer to the problem. So anyway, in the next iteration of this interview, we're actually going to walk through what this system will look like in practice and what the problem we face is in reality. So we're going to actually look at what this system would look like in practicality, more or less. So I'm going to show you all the code and all the systems. So look forward to that one, and I'll see you all in the next one.